Okay, welcome back everyone. So today we are back on the Cool Programs Jupyter Notebook, and we are just going to be finishing off today's programs. And the reason I'm rushing here is because I recorded this and I was almost finished, except basically I just got, my connection just got interrupted or whatever. I guess the recording just stopped. It couldn't handle it. I guess it was just getting too long or something. It is a free screen recorder after all. So today we're just going to finish this off, and hopefully I can finish this fairly quickly. Firstly I want to start off with actually redoing the system of three equations calculator, and I want to make it system of n equations calculator. So using n by n matrices. And this is actually more simple than you would probably expect. So let's define the we'll call it system. I don't know what to call it. Calculator. Okay, that's good enough. Probably not very descriptive, but it's better than nothing. And essentially, we'll just take in the matrix form, matrix on left. I'll show you what I mean by this in a minute. And then we have our vector on right. Okay. And just test something. Okay, should be working okay. And essentially what I mean is that, well, basically, let's see. So let's grab this tool. Basically what I mean by this is if we have some arbitrary system of equations, so for example this here, I'll just close some tabs to free up some space, equals -5 for example, and then -2x minus 4y, oh this should be y here, equals -8 for example. And essentially, basically we take all these coefficients of our variables, put them in matrix form, and then 2, 5, minus 2, minus 4, obviously multiply by our variables. And for convenience sake, the user won't have to input the variables. They'll just have to input the matrix here and the vector here. So column vector -5, -8. And this is, you could prove this by yourself, this form is equivalent to this form using matrix multiplication, right? So that user inputs this and inputs this. So this is the vector on the right and the matrix on the left. That makes sense, right? Okay. So we'll just define this as, and we'll actually call our matrix A equal to np.array, and the matrix on the left. And by convention, we call this A and then X equals B normally. And we're defining this is our A, this is our B, and our solution is going to be our C. Take the inverse of the matrix A on both sides, and that's your solution. Okay? And then we call our B equal to np.array, vector on left, on right, sorry. And our X here, capital X, we'll call it. X is just going to be np.solve linear algebra, and we take in our A and our B, and we should just be able to return our X now. So we can test this out. So we can just print it out, and we can just input some arbitrary matrices. So first we input our matrix on the left and then our vector on the right. So let's try this out. So -2, 4, for example. Obviously this is our 2 by 2 matrix. for example, and obviously it could be in by n. Let's do 3 by 3, just for fun, even though it'll take longer. Oops. Okay. And then 2, 5 minus 3. And then we can have, I don't know, 5.5, 3, I guess, and then minus 4. I'm just pressing random numbers on my keyboard. And then we have our vector, column vector. So we have, I guess, 5, 4. I'm just not going to say it because I'm probably going to get it wrong since I'm not really looking at my keyboard. And let's have a minus value here, so like, or maybe minus, like a minus float number, 0.5, maybe 0.2. Okay, so hopefully this should work. So let's run that. Run this first, of course. Attribute error, numpy, no attribute solve. Maybe, usually I forget this command. Maybe it's just, maybe that. Oh, yep, there's our solution. Okay, great. Now I don't really have time to prove it, because that'll make the video way too long. I could put it into parts, maybe I'll come back to this later. But let's just get on to the next one. So here, as you remember, we've worked with our derivative calculator using the definition of derivatives. That was fairly easy, and we'll get on to its counterpart, which is the antiderivative or the integral calculator. In this case, we're going to work with definite integrals. So let's define our integral. And before this, I actually wanted to define a function first to make life easier. So we'll call it f of x, and we'll just return like, let's just say x cubed, change things up a bit. Define our integral calculator, and we'll just take in x naught, x final, and number of rectangles. We'll abbreviate it with num of rect. Right. And I don't have much time to explain it because I want to go as quickly as possible. So let's do this. So let's define our rectangle width, and that's just going to be, well, we're just using the definition here, so it's just going to be x final minus x naught all over, number of rectangles. So I should have spelled that. Oh, forgot the capital. Oops. What am I doing? Okay. And basically, I guess I can explain this quickly. I need to do it as quickly as possible. Let's have our axes, thicker brush, our axes here, and we'll have like a graph of x cubed approximated. It's pretty bad, but it's a decent try. And let's pretend this is our let's pretend this is our x naught and this is our x final. And the difference, well, here this is our x naught. We can think of this as our x naught, and this is our x final. And if we take the difference, if we subtract x naught from x final, we just get this this business here. So all of this in the middle, and this is what we want, right? Because we'll have our boundaries here like so, and then we'll have our rectangles, and we're assuming that the width is actually constant, and I'll get to that in a little bit. So this just goes on. Pretend there's no space in here. We want as many as possible to get the best approximation. And basically, if the width is constant and we know the number of rectangles, right, because these are inputs to the number of rectangles, all we have to do is take all of this area, right, divide it by the number of rectangles, and that'll give us, well, that'll just give us our width here, right? So hopefully that makes sense. It's just pretty intuitive in my opinion. Okay, so let's continue here, and let's also initialize value, we'll call it rectangle summation, and we'll initialize it at 0 because we're going to sum up all of the rectangles. And we'll make a for loop, so for I in range rectangle summation. We might want to add a +1 here, but I think I'll do this to be safe. Okay, and basically, for in range rectangle summation +1. Oh, that's wrong. It's supposed to be number of rectangles. Number of rectangles +1. And essentially, I takes out all the parts. I will gradually, so this for loop will gradually set I equal to all the values that number of rectangles takes place. So obviously the range, so from 1 to whatever the user chooses, right? And we'll essentially define the height here. So we'll call it rectangle height. And we'll set that equal to. Basically, we just want our x0 here. So we have our x0, because if we start at the origin, we won't get good approximations, right? So we initialize this at x0. Right, so that's the first point. And we want to add to this the width scaled by some constant. So we'll get to, so that we will get to, and since I in this case represents all the values, the number of rectangles, it'll go to all of these rectangles, and if we take f of this plus I times the width, we'll basically be able to define all of the heights of these rectangles. So hopefully that very concise explanation makes a bit of sense. So we just have I times our rectangle width. Okay, and let's continue here. And of course we'll just, well, this is the obvious part, we'll define our rectangle as our rectangle height times our rectangle width, okay, or the other way around. Multiplication is commutative. We're doing pretty well on time, actually. And essentially we can just sum the rectangles. So rectangle rect summation plus equals obviously our rectangle, right? Or this is just equal to rectangle summation equals rectangle summation plus rectangle. Okay, this is just a concise way of putting it. And we can just return, we'll return our rect summation. Let's see if this works. So let's add a new tab here, and we'll have our integral. We'll do it on simple. We'll have a simple idea here. So that we can easily compute it to check it. So from 0 to 1, and we have a number of rectangles. We'll just have 1,000. So that's a decent approximation. So let's run that. Okay, we get approximately 1.5. Looks pretty good actually, because if we go over here, we have x cubed, right? So we just have the integral from 0 to 1 of x cubed dx, right? And this is just equal to, well, it's just going to be equal to, what's the antiderivative of x cubed? It's just x to the 4th, 1/4 times that, evaluated in this case from 0 to 1. So plug in 1 first, we just get 1/4, and then minus, or plug in 0. All in all, we just get 0. So 1/4 is our direct value for the area. And look at this, we just get 0.25, blah 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 blah. And it's obviously a pretty good approximation because obviously the decimal form, 1/4. All of you know this, but it's just 0.25. And this is a very close approximation. And as you can see, if we add more zeros here, we get a better and better approximation. Okay, So you can run this again. As you can see, it's getting closer and closer to 25. So hopefully that was pretty interesting. And let's move on to our Taylor polynomial of cosine of x. So for this, let's just define a function. We'll call it diff function, and we'll take in values of u, okay? And it's just going to be sim dot diff. So this is just the SymPy differential, so derivative. So it's much more simple than the derivative calculator using the definition, so that we can speed things up. And it's just going to return this, right? Okay, this is just to make things concise. And actually, yeah, that works. We'll define another function. Let's see here. Let's see, so what are we going to do here? Okay, we'll leave it like this for now then. So, oh yeah, and then we also want to define our, we'll call it d of x, and that's just going to be, we'll just, obviously it's the Taylor polynomial of cosine x, so we'll just return cosine of x, and we have to have our sim here for this to work. Okay, and we'll set our u1 equal to, u1 equals, we'll have, let's just say diff d of x, okay, so that should just work, because we have our function here and we're plugging d of x, which is just our sim dot cosine of x, right, and then we'll just have our u1, u2 equals diff u2, so this is where it starts. We'll have a decent approximation to this, so we'll have 4 terms, theoretically, or actually 5 terms, which is fine. So diff u3, or u2, sorry, and this is supposed to be u1, and then u4 equals diff u3. Okay, that's good enough in my opinion. And we'll define our Taylor polynomial, so we'll call this t. Right, we don't have to input anything. And then we'll just simply return. Oh yeah, and there's actually some more complicated things to do with this. We'll define our fact list, so sort for factorial. Fact list equals, and we'll leave it blank for now. So we'll essentially initializing it at that, and we'll have a for loop. So for I in let's say range. So we have multiple terms. We have let's see. So for in range 1, 0, and let's see. So it should just be 5. Yeah, should be correct since we have 5 terms, and this is just going to be this term minus 1, so it's from 0 to 4, and that's just 5 terms. Okay. We just want to do essentially fact list dot append should just be factorial. So I think the syntax is math.factorial of I. Right, fact list dot append math.factorial of I. And that should be correct. Okay, so that should be all of that. Yep. Okay, and this should just return, well, if you know anything about Taylor series, obviously I'm making a series on it, so I'm not going to go into the specifics on this. And I'm actually going to leave this to part 2 since my video is actually getting fairly long. So I'll see you in the next video. It's probably going to be fairly short because we don't have much to do. I just really don't want my video footage to get corrupted this time because this has gone pretty well. So hopefully you enjoyed, and I'll see you in the next part. Bye bye.